The outer layers of giants are tenuous, held weakly by gravity. They shed material in steady winds or violent eruptions, creating shells of dust and gas. These outflows enrich the surrounding interstellar medium with heavy elements. Every molecule of oxygen you breathe, every atom of carbon in your body, once came from stars like these. Our own sun will one day follow this path. In about 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, and possibly grazing Earth's orbit. Its surface will shimmer with convection cells the size of continents. Its light will redden, dim, and flicker. Eventually, it will cast off its outer layers entirely, leaving behind only a small, hot core, the next stage of stellar life. When the outer layers of a red giant drift away, the remaining core is left exposed, blazing white-hot against the dark. It's no larger than Earth, yet it holds the mass of a sun. This is a white dwarf, the quiet heart that remains when a medium-sized star like ours finishes its work. It no longer burns hydrogen or helium. Fusion has ended. The light that remains is the slow, cooling glow of heat trapped within dense matter. At first, it shines brilliantly, the surface tens of thousands of degrees, but over billions of years it fades, slipping down the long slope of time toward darkness. The matter inside is strange. Electrons packed so tightly they create an outward pressure that keeps the star from collapsing further. This is called electron degeneracy pressure, a delicate balance that can hold the star stable for longer than any human mind can easily imagine. If you could stand on its surface, gravity would pull 1,000 tons for every step you took, yet the star would look small and peaceful from afar, a point of white light, a cosmic ember. Some white dwarfs live in pairs. When two orbit closely enough, the larger can draw matter from its companion. The flow of gas forms a bright accretion disk, heating as it falls inward, and sometimes the white dwarf erupts in a sudden flash of renewed fusion, a nova. The brightness surges, outshining whole galaxies for a few hours or days before settling again. If enough matter piles on, pushing the mass past a critical limit, about 1.4 times the mass of our Sun, the dwarf can no longer support itself. Gravity wins completely, and the star detonates in a thermonuclear explosion known as a Type Ia supernova. These explosions are so consistent in brightness that astronomers use them as cosmic mileposts to measure the expansion of the universe. A single event can outshine every other star in its host galaxy combined, yet in the heart of that violence lies a kind of precision. The death of a white dwarf becomes one of the most reliable rulers in all of cosmology. Not all stars die so quietly. For the most massive, the end is something else entirely. Deep in their cores, fusion builds heavier and heavier elements until it reaches iron. Iron cannot fuse to release energy. It only absorbs it. At that instant, the balance that has held the star steady collapses. The core implodes in less than a second, crushing atoms until protons and electrons merge into neutrons. The outer layers, still rushing inward, rebound off the dense core and blast outward at 1/10 the speed of light. The shock wave tears the star apart. This is a supernova, a burst so powerful that for a brief moment it can outshine an entire galaxy. The light travels for millions of years, carrying with it the ashes of the star's life: gold, silver, calcium, oxygen, the building blocks of planets and people. Supernovae are the universe's way of recycling matter. Every atom of iron in your blood was born in one of these explosions. Every element heavier than helium owes its existence to dying stars scattering their insides across the void. When the fireball fades, what remains is either a neutron star, or, if the mass is great enough, a black hole. A neutron star is an object of unimaginable density. Imagine squeezing the sun until it's the size of a city. Inside, matter exists in a form we can barely describe. A superfluid sea of neutrons, spinning, magnetized, humming with energy. Some neutron stars spin hundreds of times per second, sending out beams of radiation that sweep through space like lighthouse beams. When those beams cross Earth, we see them as pulses of radio light. We call them pulsars. Their precision rivals atomic clocks. They spin with such regularity that the tiniest deviations can reveal the presence of planets or the ripples of gravitational waves passing through space-time. The magnetic fields around them are trillions of times stronger than Earth's. A single spoonful of neutron star matter would weigh more than Mount Everest. Yet, despite this crushing gravity, they can remain stable for billions of years, slowly spinning down, radiating their stored energy into space until they grow silent. In even more massive stars, collapse goes further. Gravity overwhelms every known force. No pressure can stop it, not even the degeneracy of neutrons. The core shrinks beyond any physical surface, forming a singularity, a point where density becomes infinite, and our laws of physics lose their meaning. Around it forms an event horizon, a boundary beyond which nothing, not even light, can escape. This is a black hole, the ultimate end for the heaviest stars. From a distance, a black hole doesn't look like much, only the absence of light surrounded by swirling gas. Yet, near the horizon, gravity warps time itself. To an outside observer, a falling object seems to slow, never quite crossing the edge. To the object itself, time continues normally, plunging inward to an unknown fate. The material that falls in forms an accretion disk, heating to millions of degrees as it spirals closer, emitting X-rays and jets that can stretch across galaxies. These jets are among the brightest phenomena in the universe. Some black holes merge, colliding in cataclysmic unions that send ripples through the fabric of space-time. Gravitational waves that we can now detect on Earth. Tiny tremors revealing the dance of invisible giants billions of light years away. And yet, black holes are not the end of everything. Over immense spans of time, they may slowly evaporate through a faint process known as Hawking radiation, leaking energy back into space until nothing remains but a whisper of heat. In the grand timeline of the cosmos, even these titans are temporary. The universe is a master recycler. The matter thrown into space by dying stars drifts outward, mixes with cold clouds, and forms new generations of suns. Every birth depends on death. Every spark comes from the ashes of what came before. When we look at a bright star, we're seeing the recycled light of countless ancestors. The calcium in your bones, the oxygen in your lungs, the gold in a ring. All of it was forged in stellar hearts that lived and died long before Earth existed. The universe is not separate from us. We are its continuation. Somewhere in the galaxy right now, new stars are forming from the remains of old ones, and in billions of years, those stars may have planets, and those planets may have life that looks up and wonders where it came from. This endless cycle, birth, burning, collapse, renewal, has been running for nearly 14 billion years. If we project forward, the story stretches even further, into epochs we can only imagine. As the universe ages, fewer massive stars are born. Gas becomes scarcer. Galaxies grow dim. Red dwarfs, the smallest and most efficient of all, will dominate the sky for trillions of years. They burn their fuel slowly and steadily, glowing faintly but enduring longer than any other kind of star. Eventually, even they will fade. The last red dwarfs will cool and turn into black dwarfs, cold, dark remnants drifting through the void. When the final fusion reactions flicker out, the universe will enter an age of darkness. The remaining white dwarfs will cool to black. Neutron stars will lose their spin. Black holes will evaporate. On a timescale so vast that numbers lose their meaning, all the light will go out. Physicists call this the heat death of the universe, a time when entropy reaches its maximum and no more work can be done. The cosmos will still exist, vast and cold, but without new stars, without warmth, without change. Yet, even in that distant future, the memory of starlight will remain written in the fabric of space itself. Every photon ever released, every wave of radiation, every whisper of gravity will still echo faintly through the dark. And perhaps, if the universe is cyclical, as some theories suggest, that darkness will one day give way to another beginning. Matter may condense again. A new burst of light may follow. Another cosmos may bloom where this one fades. Whether that happens or not, the story we know is already enough. It tells us that everything that exists, every planet, every mountain, every living cell, is made of the same materials born in the hearts of stars. When you look at the night sky, you are looking into your own ancestry. You are made of hydrogen, helium, carbon, oxygen, nitrogen, iron, all gifts of stellar furnaces long extinguished. The atoms in your hands are older than the Earth itself. They have drifted through galaxies, through nebulae, through stars that lived and died, before finally coming together to form you. That connection is not poetic exaggeration. It is literal, measurable truth. The same physics that shapes galaxies has shaped your cells. The same gravity that gathers dust into stars holds you to the ground. The life cycle of stars is not just a story about distant suns. It's the story of us, of how the universe became conscious enough to look back at itself and wonder. So, when you lie down tonight and close your eyes, think of the quiet clouds where new stars are forming. Think of the ancient light that has traveled for billions of years to reach you. Think of the gentle balance that keeps suns alive and the inevitable peace that follows when their fire goes out. Somewhere, a new star is taking its first breath of fusion, while another is releasing its final one into the dark. Between them lies everything: worlds, life, memory, and the slow, patient rhythm of creation. The universe is vast, but it is not distant. It is within you, and you are within it, endlessly recycled, endlessly new. And if this thought brings you calm, let it stay with you as you drift toward sleep. Like the light of a star crossing the darkness, your thoughts can travel far, lighting quiet corners of the cosmos that may never be seen again. Thank you for listening, for resting here, for letting your mind float among the stars. If you'd like to keep exploring these gentle journeys through space and time, feel free to like, subscribe, or simply return when you need the quiet. The universe will always be here, waiting, calm and infinite, carrying you softly through the long night.